So good morning, Mr. Li.
Yeah.
So the journey is now complete. Composed with Professor Aral Chu from University of Berlin, from the Professor Rediger Haas from the University of Chalmers, Professor Susan Glaser from the University of Bonn, and both Marania Antoine from the laboratory Gilles Passud and Pascal here.
Yes.
So you have between 45 and 60 minutes to present your work.
Okay.
Thank you very much.
Okay, hello. Hello everyone. Thank you for coming. And many thanks to the jury's members. It's my pleasure to have you here for my PhD defense. Today, I'm going to introduce what I have done during my PhD study. Here at the GNSS Laboratory in University of French Polynesia, in collaboration with Wuhan GNSS Research Center in Wuhan University. This work is supervised by Professor Jean-Pierre Bahil and Professor Yi Donglou. So the title of my thesis is Relating Millimetric GNSS to Meteorology and Climatology, from world vapor field to sea level variation. I will give my presentation in the following 5 parts. So first, I will give some introductions of the background, our motivation, the aims and objects of our study. We all know that living on the Earth, the atmosphere is essential for our human beings. To study the Earth's atmosphere, we have meteorology, climatology, and aeronomy. Aeronomy is not our topic here. The main difference between the meteorology and climatology is a matter of time. Meteorology studies atmospheric processes and motions in short-time scales, for example, from several minutes to several weeks. While climatology is more concerned about the long-term statistics of variation in atmospheric conditions, which will help us to know the climate pattern over large time scales, particularly for 30 years long. Needless to say, both have crucial impacts on our human life, society, ecosystems, and the environment. Climate has been changed by the natural internal processes on the Earth continuously. However, the emission of greenhouse gases, our anthropogenic activities, etc., have accelerated this procedure. Nowadays, it's known as climate change. One straightforward impact of climate change on us is that extreme weather events happen more frequently. For example, we have hurricanes and tornadoes, heat waves with droughts, extreme precipitation with flooding, and also sea level rising. These effects of climate change are more significant here in French Polynesia, but more related to water in the atmosphere and the ocean. Located in South Pacific Ocean, French Polynesia consists of over 121 small islands and atolls. The Polynesian climate is tropical and humid maritime. There are generally 2 seasons, the wet season from November to April and the dry season from May to October. During the wet season, heavy precipitations and flooding events happen frequently. And due to the geographic positions, all the islands here are exposed to tropical cyclones and also sea level rise. For example, Tahiti is a volcanic island. The mean annual precipitation on its western coast is about 1,500 millimeters per year, but can reach up to 10 meters per year on its reliefs of its eastern coast. The spatial topography and small watersheds make it more likely to have flash flood events on the island. To have a better knowledge of these extreme events, here in our study, we mainly focus on 2 objects. The first one is absolute sea level variation. It's one of the key global climate indicators, as it increases the risks of losing land for low-lying small islands and threatens human living in the coastal area. A lot of attention needs to be paid in the long run, especially here in French Polynesia. The second one is the water vapor content in the atmosphere. Water vapor is water in the gas phase of the air. Although it only takes 1% total amount of the gas, it provides over 99% of atmospheric moisture and is responsible for about 75 total greenhouse effects. It plays a vital role in the Earth's atmosphere systems like hydrological circle, energy balance, climate change, and the development of weather systems like the heavy rainfall here. Moreover, it can cause radio wave signal delays in space geodesy. To observe absolute sea level variations, satellite altimetry is widely used on global scale. For example, we have satellite altimeter mission, JSON-1, JSON-2, and so on. A more general way is to use a TED gauge collocated with GNSS. Nowadays, we have more and more GNSS-based techniques like GNSS reflectometry, GNSS buoys, and GNSS unmanned surface vehicles to measure sea level directly. While for atmospheric water vapor content, there are mainly two kinds of observation techniques. The first group provides in situ observations. For example, the ground-based weather stations and the radio sound. The second group uses remote sensing techniques like the spaceborne water vapor radiometer, the airborne Ramlanda, and ground-based water vapor radiometer, and also GNSS receiver. As we can see, GNSS is nowadays one of the most promising tools in both meteorology and climatology studies. With the development of GNSS over the years in terms of the two objects in our study, here we aim to find out first, what precision we can achieve with current GNSS techniques. Secondly, how to apply the high precision GNSS positioning technique to obtain the sea level variation over Polynesia. And thirdly, it is possible to retrieve the three-dimensional water vapor field overhead from a standalone GNSS station. To answer the first question, here we come to part 2, millimetric GNSS and its error budget. First of all, let's have an overview of the global navigation satellite system, GNSS. Nowadays, we have 4 global constellations. They are GPS by the US, Galileo by Europe, GLONASS by Russia, and BDS-3 by China. The basic principle of GNSS is that the receiver on the Earth receives GNSS signals transmitted from satellites and make range measurements between them. Thereafter, GNSS positioning can be achieved using triangulation. There are generally 3 types of measurements in GNSS: carrier phase, pseudo-range, and Doppler. Among them, carrier phase measurements are widely used for high precision applications because of their millimeter level accuracy. In terms of high precision positioning, today we have techniques called real-time kinematic positioning, RTK, precise point positioning, PPP, and the combination of them called PPP-RTK. Shortly speaking, the RTK technique has a high accuracy at centimeter or even millimeter level, but is limited by the requirement of a reference station nearby. While PPP technique can be applied to any standalone GNSS station, and the centimeter level accuracy can be expected. However, it usually takes a long convergence time to resolve the so-called phase ambiguity. To combine the advantages of both techniques, the PPP-RTK technique has been developed over the years, which uses a local GNSS network to provide additional error corrections. But here, in our study, we use the GNSS PPP technique because of its high precision and easy to implement. Although we have carrier phase measurements that are at millimeter level, there are a lot of error sources that prevent us from getting the true geometric range between the satellite and the receiver, as shown in the observation equation for carrier phase. For example, we have satellite orbit arrows DORB, satellite clock offset DT, and satellite instrument delays DPCO, DPCV, etc. Here, we will only introduce 4 of them to give an overview of the error budget of GNSS PPP. They are satellite orbit arrows, satellite clock offsets, tropospheric delays, and phase ambiguity. The position of satellite is necessary for GNSS positioning. It can be calculated from the broadcast ephemery, but limited by the imperfect model in orbit determination and the low update interval. The accuracy of current satellite orbit broadcast ephemery is at millimeter levels, which is not applicable to high precision applications. To improve the accuracy of satellite orbits, we need a more advanced model for those non-gravitational forces, for example, the solar radiation pressure shown in the figure, and also observations from the global ground-based observation network to mitigate errors in precise orbit determination. Thanks to the continuous efforts of International GNSS Service, or called IGS or MGX, they have been working on this since the 1990s. Nowadays, we have the final precise satellite orbit products that allow us to improve the accuracy from 1 meter level to 2 to 5 centimeter level, as shown in the table. Time is also one of the backbones of GNSS. Atomic clocks have been used on board GNSS satellites, like cesium, rubium, and hydrogen meso clocks. Although these atomic clocks have relatively high stability, the clock drifts and variations of atomic reference frequency are inevitable over time because of their nature. To enable the virtual synchronization of all the satellite clocks, these clock offsets and drifts are estimated and predicted by the control center on the ground and provided in broadcast ephemery. But even after applying those corrections in broadcast ephemery, the accuracy of satellite clock, typically within 2 to 5 nanoseconds, is still not sufficient for high precision applications. Similarly, more precise clock products can be estimated from a global GNSS network. Nowadays, we have precise satellite clock products estimated and provided by IGS, the accuracy of which can reach up to 0.1 to 0.2 nanoseconds, and even better. Before being received by the receiver, GNSS signals will pass through the Earth's atmosphere. The troposphere is located in a range of 0 to 16 kilometers high. Generally speaking, it consists of dry air and wet air, or called water vapor. Both introduce refractions and delays in GNSS signals, which is typically 2 to 3 meters in the zenith. Therefore, the total tropospheric delays are usually divided into 2 components, the hydrostatic component and the non-hydrostatic or wet component. Both are integrals of refractivity along the repath S. But here, ND is the dry refractivity and NW is the so-called wet refractivity. Since these delays are independent of frequency, these 2 components are usually modeled in a similar way in GNSS PPP. For example, the wet component, or called slant wet delay SWD, is often modeled with a zenith wet delay ZWD together with the mapping function MF representing the delays in line of sight direction, as well as 2 horizontal gradients GN and GE describing the azimuthal anisotropy. Usually, these 3 parameters are estimated as unknown in GNSS PPP since SWD is highly variable. Where for the hydrostatic component, more often we have precise models, for example, subharmonic model. Although these 2 components are corrected in different ways, the residuals are at the same level of 2 to 7 millimeters. Another error source that needs to be mentioned is the carrier phase ambiguity NF. It's an unknown integral in carrier phase observations as shown in the figure. Biased by the atmospheric delays and hardware biases, its integral property is lost and cannot be well resolved with a conventional PVP model. In this case, only float ambiguities can be resolved, and the centimeter, even decimeter level positioning accuracy can be expected after a long convergence time, for example, 30 minutes as shown in the figure. By correcting the signal phase biases, one can implement the so-called PVP-AR to solve the integral ambiguity within a short convergence time. By introducing additional atmospheric delays, one can use PVP-RDK technique to get a better solution. In general, the accuracy converges to 1 to 2 centimeters in 10 minutes as given in the figure on the right side. There are also many other error sources in GNSS PVP. Here we just give a list of them. Different methods can be applied to model or mitigate them. The residuals vary from millimeter level to the centimeter level. Well, for the title corrections, we have correction models that are suggested by RERS 2010 convention. In this part, error sources and their budgets of GNSS PVP were revealed. Some of the state-of-the-art error mitigation methods were introduced. However, the error budget of PVP is not just a simple list, but a cascading process, since some of them are highly correlated. The positioning accuracy that generally we can achieve at present depends on the positioning techniques. For PVP-AR or PVP-RDK, millimeter level positioning accuracy is achievable in 10 minutes, where for PVP with float ambiguities, the positioning accuracy is at the centimeter level. With the development of low Earth orbit constellation LEO, faster and better positioning solution can be expected with the future LEO augmented GNSS. This real work has been published in the journal Service in Geophysics with Professor Shi and Professor Zhang. But here, in our study, the high precision GNSS positioning technique allows us to derive level variations because the vertical land motion at the target station can be extracted from the long-term high-precision GPS PVP position time series. Where for retrieving the water vapor field, multiple spherical wave delays will be available with the multi-GNSS and future LEO constellations, which also motivates us to find an advanced model for correcting those tropospheric delays. Next, we come to part 3, monitor absolute sea level variations over fringe Polynesia. To observe and monitor absolute sea level variations, there are two commonly used techniques. The first one is satellite altimetry, developed since 1993. It observed absolute sea level variation, delta ASL, by measuring the two-way distance between the satellite and the sea surface. Although it has a good performance in the open sea, the accuracy decreases and even not available near the coast. Another technique is using targets collocated with GNSS, also known as GNSS-TG. Targets have been widely used to record sea levels over the world since the last century. However, it can only measure the relative sea level variation, delta ISL, with respect to the benchmark. This is because the benchmark itself undergoes various vertical motions at the same time. Therefore, we need a collocated GNSS receiver to monitor those vertical land motions, or called VLM, so that we can get the delta ASL by adding them together. But here, we will mainly focus on the VLM, since the delta ISL has been investigated in a previous study published in Geodesy and Geodynamics by Professor Dekan. The VLM usually can be obtained in 3 ways. One is using the prediction model based on glacial isostatic adjustment GRA. The GRA describes the viscoelastic relaxation in response to the redistribution of ice and water on the Earth's surface. As a result, it mainly considers processes in a global scale, and no local processes are included. Another one is directly differentiating delta ASL from satellite altimetry and delta RSL from TED gauge. As we introduced before, this method is limited by satellite altimetry in itself. A more precise way is to derive VLM from geodetic observations. Among them, GNSS is relatively low cost and makes continuous improvements in precision. Therefore, it has been widely used to derive VLMs. In our study, we used the 5 category station in French Polynesia to monitor sea level variation. Since 2007, these 5 category stations have been built in different places, including Tubuai, Waihau, Hangihua, Akimo, and Higitia. A typical target is shown on the right side, for example. We have radar and pressure sensor to measure the delta RSL and the collocated GNSS to monitor the VLM. Until now, we are supposed to have observations for over 12 years. To obtain the absolute sea level variation at all the target stations, first we need to derive VLM from the GPS datasets. This procedure can be divided into 5 steps as given on the left side. The first step is GPS data collection. If we look at the GPS data availability at all the target stations, as shown in the figure, data gaps can be found at each station. To get a reliable VLM estimate, as suggested by previous studies, we decided to take two data requirements. 1, 3 years of data without discontinuities. 2, the ratio of data gap is less than 30%. Only 3 of them satisfy these 2 data requirements. They are station TBTG, VRTG, and RKTG. The second step is processing GPS dataset collected at all the target stations from 2009 to 2021, as well as 66 well-distributed IGS stations. The station distribution can be found on the right side. Here, this IGS station is used to align all our positioning solution to a common terrestrial reference frame, that is IGS R3 in our case. The GPS PVP technique was adopted using software Panda, where the state-of-the-art error models were adjusted as listed in the table below. After GPS data processing, we will obtain a long-term position time series, which can be modeled with the formula given below. In general, this model can be divided into 2 parts, the function model and the stochastic model. Specifically, in our case, for the functional model, we use the linear trend B and the intercept Y0 to describe the linear variations, and trigonometric functions to represent the periodical signals, including annual, semi-annual, seasonal, and the GPS geokinetic year signal. Possible discontinuities in the time series are considered by the Heaviside step function. Since the noise in GPS position time series is time correlated, we use power low noise plus white noise for the stochastic model. All these parameters were estimated using maximum likelihood estimation approach with software capture. Among them, the linear trend B is exactly the VLM estimates that we want. Finally, with delta RSL, we can obtain the absolute sea level variation delta ASL by adding them together. Following all these steps, we estimated the VLMs at 3 target stations. First, at station TBTG located in Tubuai Island, we got an estimate of minus 0.92 millimeter per year. The first figure shows the original position time series with blue dots and the modeled ones with red dots. The estimated VLM is also plotted with a green line here. Overall, our model fits the original position time series well. This can also be verified in the residual time plot as shown below. The statistical histogram of the residuals show a mean of minus 0.02 millimeters and a root mean square RMS of about 6 millimeters. The VLM estimates at station VRTG located in Waihau is minus 0.49 millimeter per year. However, our estimated model doesn't seem to fit the original time series as well as we expected. As can be seen from the original time series, dip gaps are large and happen frequently. Several offsets that are mainly caused by instrument change are indicated by the gray dashed line in the figure. We suspect these are two possible reasons for this non-robust estimates. Well, at the station RKTG located in Pekitia, we got an estimate of -0.43 millimeter per year. The good performance of our estimated model can be found in both the original position time series and the residual plots. Now, with the WLM estimates, the trend of absolute sea level variation can be obtained by combining the delta ISL derived from a previously published study. As listed in the table, the trend at station RKTG is 1.52 millimeter per year. At station TBTG, the trend is 5.25 millimeter per year. And at station VRTG, the trend is 3.62 millimeter per year. To validate our results, we compare them with those trends derived from satellite altimetry. The values are shown from 6 data groups are shown in the table below. Taking the means as a reference, we found that our results have a good agreement at station RKTG, but overestimate at station TBTG and VRTG. To summarize, in this part, we estimated the WLMs and obtained the trend of delta ASL at 3 target stations. All the estimated WLMs are negative, which can be ascribed to the thermal subsidence. And sea level rising is observed at all the target stations, which is closely related to global warming. However, discrepancies in trends between our results and those from satellite altimetry exist. There are several possible reasons. First, we use different time spans. Secondly, the internal variability of the climate plays its role over various time scales. For example, over short time scales, we have swells and currents. Over large time scales, we have interdecadal Pacific Oscillation, IPO, and El Nino Southern Oscillation, NSO. Mismodeling of WLMs could also lead to discrepancies. Besides, those trends from satellite altimetry were not extracted from the exact location of the target station, which may introduce a set-dependent systematic errors. Nevertheless, a possible pattern of IPO in the South Pacific Ocean was indicated by our results. As shown in the figure, our trend estimates at a station located in Tuwai Island is much larger than the other two located in the north. This work was published in the journal Geodesy and Geodynamics with Professor Deacon and Dr. Hopper. So next, we come to part 4. I will introduce how to retrieve the 3-dimensional water vapor field from a standalone GNSS station. Today, we have several ground-based techniques to observe 3D water vapor field. One is using the radio sound network. It provides in situ observations on global scale with stations distributed over the world. However, the resolution is low because the balloons are typically launched twice a day. By measuring the thermal emission from gases and hydrometeors, the water vapor radiometer, or called the WVR network, can remotely sense water vapor in the low atmosphere. But it's highly technical and expensive. Regular calibrations are needed, and systematic biases have been found when compared to other techniques. Another remote sensing technique is called the water vapor differential absorption LiDAR network. Different from WVR, this LiDAR is an active instrument that retrieves water vapor from its absorption spectrum. However, it has similar drawbacks as the WVR network. GNSS tomography is an alternative way where the water vapor field is retrieved from the GNSS signal delays that are caused by water vapor in the troposphere. It can be operated in all weather conditions, but usually a dense GNSS network is required, which means it's high cost and its spatial resolution is limited by the interstation distance. Besides observation techniques, we have other methods to derive 3D water vapor field. By assimilating observation into the numerical weather model, NWM, one can resolve the fundamental atmospheric variables over global or regional scales, including the water vapor. However, the resolution is often tens or hundreds of kilometers, and a supercomputer is usually necessary to run the model. Another way is to apply atmospheric turbulence theory, since the turbulence theory describes the correlation between atmospheric variables. But until now, only simulation studies are available. Now, if we consider a single or a few observation stations in a relatively small region, for example, here in Tahiti, how can we obtain a 3D water vapor field with a high spatial temporal resolution? As we introduced before, there are several possible solutions, but they are either high cost or come with a low resolution. This motivates us to find a new method to retrieve a high resolution 3D water vapor field from a standalone GNSS station. This method can be applied in some cases where the GNSS network is not available, for example, in island countries, and could also provide us with an advanced model for tropospheric delays. With only one standalone GNSS station, GNSS PVP technique is often used. As we introduced before, the SWD, which is defined as the integral of weather refractivity NW along the repath S, is often modeled with zenith weather delay ZWD, horizontal gradients, and mapping functions. Thereafter, the estimated DWD or SWD can be converted into the integrated amount of water vapor IWA, according to GNSS meteorology. But in this way, only one-dimensional integrated values are derived, and a strict separation between the horizontal and the vertical direction is assumed in this model, which cannot represent atmospheric processes in relatively small scales. For example, the turbulent motions. To give a more realistic model, here we propose a new method. Assuming hydrostatic equilibrium in the atmosphere, the ideal weather refractivity NW bar takes an exponential decay along the altitude, as indicated by the yellow line in the vertical profile. To take those turbulent motions into account, we propose to add a small term epsilon to the exponential model of NW bar, as shown in the vertical profile with the blue line. This method allows us to have a new model for SWDs as shown below, where SW bar is the delays caused by ideal weather refractivity NW bar. The 3D sonic functions are then used to represent the perturbation epsilon in the spherical coordinates as shown in the formula below. Here in this figure, I show the two-dimensional sonic functions that are orthogonal on the unit disk. As we can see, several sine cosine-like functions are used here to represent the variations on the disk. Extending to 3D case, we will have 3D sonic functions over the unit ball. And the standalone GNSS station is located at the center of the disk here, or at the center of the ball in the 3D case. Here we use the 3D sonic function because they provide a more physically reasonable model with the orthogonal function basis over ball, where the spherical harmonics YLM represents the multi-layered atmosphere, and the radial polynomials RNL takes the largest variation of weather refractivity along the altitude. More importantly, they allow us to express the SWDs in an analytical way. However, this procedure is highly technical. Here we just give its final matrix form, where GI is the design matrix of SWD, and P is the vector of unknown PNLM of sonic functions in the model of epsilon. In practice, we have SWDs as input signals, and the parameter P of sonic function need to be resolved to retrieve the perturbation epsilon. However, this is a typical radon inverse problem, which is endogenously ill-posed. To solve this air-posed problem, additional physical information is required. For example, the covariance matrix of parameter P, COV, P. Thereafter, the technical regularization method can be applied to solve the parameter P caret as shown on the right side. This a priori information can be derived from the statistics of the wet refractivity field, or SWDs, in several different ways. First, based on atmospheric turbulence theory, one can derive it from the refractive index structure function. But empirical parameters and several physical assumptions are usually underlined in this function. Since SWD is often modeled with ZWD and horizontal gradients, we can also obtain the information from them. But previous study mainly focused on 1D or 2D time series analysis, which cannot represent the 3D wet vapor field. A third way is deriving from NWM statistically. Once again, their resolution are currently too close to be applied to small areas, for example, 5 to 10 kilometers. Fortunately, according to a study published by Zhang et al., we can obtain the information from the statistics of GNSS derived SWD from periodic sets. In their work, an almost stationary process SE is formed by multiplying SWD with the sign of elevation angle here. By modeling this process with spherical harmonics YLM and the trigonometric function Pn, a correlation time of up to 4 days and an angular correlation length of about 20 degrees were found statistically, as indicated in the green dashed line in the two figures. This a priori information is derived from the periodic set and will be adopted in our study. For simplicity, we approximate this spatial covariance function with an exponential function shown on the right side. Here, psi is the spherical distance in degree, and delta zero square is the variance of SE in millimeters square. Besides, an additional constraint for parameters is needed. According to Password's theorem, we have Coulomb rule in geopotential field study. That is, the degree variance delta L square is proportional to the inverse cube of the degree L. Similarly, a Coulomb-like rule is expected in our case. We propose that the sum of the square of the parameter over the order m is proportional to a over the degree to the power of alpha and L to the power of beta. In practice, all these parameters, A, alpha, and beta, can be determined from the spectral analysis of the wet refractivity field. However, so far as we know, no such studies are available. Current NWMs are promising, but somehow limited by their low resolutions. Nevertheless, spectral analysis of other atmospheric variables, for example, the temperature anomalies and the wind field, have suggested that alpha and beta are equal to 2, and A is case-dependent. To validate our proposed method, here we did a simulation study. The simulation area is the hemisphere overhead a standalone GNSS station, as shown on the right side. Specifically, the area is 200 kilometers by 200 kilometers in the horizontal direction and up to the triple poles at 16.5 kilometers height. A cutoff elevation angle of 10 degrees was chosen, and 3D zonic function up to 20 degrees were adopted in our study. As for the input SWDs, we simulated over 4,000 points that are randomly distributed over the hemisphere. For simplicity, we fixed some simulation parameters into constants, like the Earth radius. In terms of our priori information, we set the variance of SE to 10 millimeters square to ensure the simulated SE signals are in physically reasonable range. Where for the Coulomb-like rule, the determination of A will be introduced later. Now, considering that we have two kinds of a priori information, the first one is the covariance matrix COV-SE for SE signals, and the other one is the Coulomb-like rule CP for parameter P. To combine them together, first we obtained the SE model from the SWE model. by using the definition of SE. Thereafter, based on the SE model, we can combine these two a priori information to derive a new covariance matrix COVP as shown in the formula below. Recording that we have A in the color-like rule matrix CP. By analyzing the singular value variations of the matrix GTG plus CP-1, we found that changing A will significantly affect the relatively small singular values. Therefore, we decided to take A to be 25,000 to surprise the decreasing pattern of small singular values. And thereafter, a more stable solution can be expected. Now, with the covariance matrix of parameters COVP, we can simulate a set of parameters PS using the spectral decomposition method. The exact values of PS can be found in the figure below. Based on the SE model, we can generate a set of SE signals with the simulated parameters PS. We also give the sky plot of the generated SES on the right side. Using the generated SE signals as input and the a priori information COVP, we can now solve the ill-post problem using Tikhonov regularization method. But here, a regularization ratio chi. We know the true value of the parameter. We took chi to be 0. Residuals, the norm of SU residuals, and the norm of parameter vector difference as shown in the figure. The reconstructed parameters PS carrots are also compared with the simulated ones. As we can see from the figure, most parameters are well resolved. Thereafter, we can reconstruct the SE signal SES carrot. Compared to the generated SE signals, the statistical histogram of SE residuals show an RMS of about 0.01 millimeters. The sky plot of the SE residuals is shown on the right side. As can be seen from the figure, most of the extreme values can be found at low elevation angles, which may be ascribed to the less constrained behavior of our model near the boundary. Next, we present the reconstructed 3D distribution of the perturbation epsilon. The generated one is also shown here for comparison. Overall, a good agreement can be concluded, and anisotropy can be found in both results. To summarize, in this part, a new alternative method for retrieving the 3D wet refractivity field is proposed and validated. Compared to the GNSS tomography, only one standalone GNSS station is required. It could also be considered as an advanced model for SWDs when comparing to the conventional model with mapping functions and horizontal gradients. Although this method is computationally expensive, parallel computing can be implemented for several stations at the same time. Well, to apply our method to real data sets, a priori information on SWDs or wet refractivity field is needed, which can be derived from the real data sets or high-resolution NWMs. A more realistic color-like rule is also required, which can be derived from a high-resolution NWM. Moreover, a more realistic observation distribution needs to be reconsidered, as well as the impact of multipath in the input SWD signals. This work has been submitted to the journal IE3 Transactions on Geoscience and Remote Sensing with Ms. Bai and Professor Zhang. It's now under review. Finally, we come to part 5, summary and outlook. Recalling that we give 3 targets at the beginning. First, we want to find out what precision we can achieve with current GNSS techniques. The error budget of GNSS PPP was therefore revealed, including the error sources and their mitigation method. In general, the positioning accuracy of PPP is at the centimeter level of the convergence. But it also depends on the observation geometry, processing strategies, etc. Millimeter level positioning accuracy can be expected with the PPRK technique. Secondly, we want to apply the high precision GNSS positioning technique to obtain the sea level variation over Polynesia. As a result, by applying GPS PPP to the local GNSS TG network, the WLMs at 3 television stations were estimated from the long-term GPS PPP position time series. The delta ASL ranging from 1 to 5 millimeters per year was then obtained. Our delta ASL results are consistent with the satellite altimetry in Hikitia, but overestimated in Tuwai and Tahiti. Nevertheless, a possible pattern of IPO is indicated by our delta ASL results. Finally, we want to know if it is possible to retrieve the 3D wide vapor field overhead from a standalone GNSS station. Hence, a new method was proposed where the fluctuations of the 3D wide refractivity field were modeled with 3D thermic functions. To solve this air-post problem, additional a priori information was introduced for regularization. The feasibility and performance of our proposed method was validated with a simulation study, where a good agreement was found between the generated and the reconstructed results. But there are still a lot of future work to do. In our study, we only use GPS PPP to derive WLM. Due to the short time span and the data gaps, we only have results at the 3 television stations. This is not sufficient to give us a full picture of the delta ASL over French Polynesia. By collecting datasets continuously at all the television stations, we will obtain a long-term multi-GNSS observations. Thereafter, multi-GNSS PPP or even PPRK with a higher accuracy can be implemented. With the development of LEO constellations, the LEO augmented GNSS could also be expected. Besides, when applying our proposed method to derive the 3D wide refractivity field, a more realistic Kula-like rule needs to be derived from high-resolution NWMs. Moreover, there are several assumptions in our simulation study need to be reconsidered. For example, the constant radius of the Earth and the street repass. Therefore, in our future work, we should perform retracing with a more realistic coverage radius of the Earth. And a new set of orthogonal function bases is preferred, considering the physical shape of the wide refractivity overhead, the real observation distribution, and also the temporal variations. Other set-dependent factors like the multipath effects should also be investigated and mitigated to ensure clean input for the modeling. In short, with the development of multi-GNSS and LEO constellations, as well as the positioning techniques, millimeter level positioning accuracy will be achieved in short convergence time with PPRK or LEO augmented GNSS. This will allow us to have more accurate WLMs and thereafter delta ASLs. Until then, a real-time high-precision sea level monitoring system over French Polynesia can be expected with the local GNSS TG network. On the other hand, the multi-GNSS together with LEO satellites allow us to have a better observation distribution overhead a standalone GNSS station, as shown in the figure below. Once we have a more realistic orthogonal function basis and a priori information for modeling, a more accurate 3D or even 4D wide refractivity field can be retrieved. Various applications in meteorology, climatology, and space geodesy can be expected. Not surprisingly, it helps to form a virtuous circle, since a better model of wide refractivity can improve the accuracy of GNSS positioning and also sea level monitoring with GNSS TG. At the end, I list all my publications during my PhD study here. There are 4 journal papers and 2 conference abstracts. 2 of the journal papers were published, while the other 2 had been submitted for reviewing. So these are all that I have done during my PhD study. Thank you for your time and attention. That's all. Thank you.